الفضاء بجامعة الملك عبد العزيز أن يستضيف في هذه الليلة المميزة أحد علماء الفلك الراديوي المشهود لهم عالمياً بغزارة إنتاجهم العلمي، حيث بلغ عدد مقالاته المنشورة 770 مقالاً، منها 450 مقالاً محكماً. كما تم الاستشهاد به 19,200 مرة. نشر مقالات في كبرى المجلات العلمية كAstrophysical Journal, Astronomy and Astrophysics, Astronomical Journal, Monthly Notice, Nature, Physics, Review Letters and Science، وكثير من المجلات. ويعمل حالياً ضيفاً عالماً زائراً في معهد ماكس بلانك للفلك الراديوي، كما عمل كعالم زائر في العديد من المؤسسات العلمية العالمية. The Department of Astronomy and Space Sciences at King Abdulaziz University is delighted to host on this distinguished night one of the radio astronomers internationally acclaimed for his abundance of knowledge. Our guest speaker is a guest scientist at Max Planck Institute for Radio Astronomy, Bonn, Germany since 2015, employment at King Abdulaziz University, Jeddah, also staff scientist at Max Planck Institute for Radio Astronomy, Bonn, Germany, between July 1982 and May 2015, guest scientist at Zhengzhou Astronomical Observatory in China between 2014 and 2019, guest scientist of the National Astronomical Observatory of Japan, ALMA Group, in Mitaka, Japan in 2014, guest scientist of the ESO ALMA Group, Santiago de Chile in 2013, guest scientist at Australian Telescope National Facility, Epping, Australia, between 2004 and 2006, guest scientist at ESO Santiago de Chile in 1997, guest scientist of the Observatory de Grenoble Saint-Martin de Hers in France in 1991, guest scientist at the Daedok Science Town, Daedok, Korea in 1987, guest scientist of the Onsala Space Observatory, Onsala, Sweden in 1986, postdoctoral at the Bell Telephone Laboratories, Homedale, USA between 1982 and 1983, postdoctoral at the University of California, Berkeley, USA in 1982, postdoctoral research position at Max Planck Institute for Radio Astronomy, Bonn, Germany between 1980 and 1982. Our guest speaker had got his PhD at the Max Planck Institute for Radio Astronomy in Bonn, titled Isotope Ratios and H2 Densities of Molecular Clouds in 1980. Diploma of Physics and Astronomy at the University of Bonn, titled Evaluation and Interpretation of the Optical and Radio Astronomical Measurements of the Interstellar Line in 1977. He also studied physics and astronomy at the University of Bonn, Germany between 1970 and 1980. His research activities: star formation, astrochemistry, active galactic nuclei, galaxy evolution, measures, late type stars, and physical constants. Honor, he got an Otto Hahn Medal of the Max Planck Society in 1981. Memberships: the International Astronomical Union, Astronomische Gesellschaft. His scientific output: the total number of ADS entries 770, 450 are refereed. He also got 19,200 citations. Hersch Index 72, Astronomy and Astrophysics 265 publications, Astrophysical Journal 110 publications. He also published articles in A&AR, AJ, Monthly Notice, Nature, Physics Review, Letters, Science, and much more. Please help me in welcoming Professor C.Henkel.
Oh, thank you very much for this very kind introduction. And I think it's a pleasure for me, a great pleasure for me to have a talk here at KAU and in Saudi Arabia. It was very nice almost 5 years ago I think it was May 2015, when I showed up, invited by you for about 10 days in Jeddah, and I had a great time and giving 5 talks there. And this talk is highly changed, but still a little bit reminding similar to one of the 5 talks I've given there, but of course with a lot of new stuff. And I think it will also be, even though it's a brief introduction into radio astronomy, it will be a little bit longer than the talk in those days. So thank you very much for this invitation. And I think I'm going into this. So I think it's shared, but doesn't work. So let me try again. I can press it, but nothing happens. I think that was different before. Mm-hmm. Oh, now it works. Great. Okay. Yeah, so I'm talking about some basics on radio astronomy. And this means telescopes, fundamentals, and science. And yeah, thank you again very much for this opportunity to give a talk here. But prior to these 3 main items of this talk, I will briefly mention the situation of the Max Planck Institutes in Germany and what they are doing and where they are doing it. So yeah, this is the map. Germany is not a very large country, but it's a very green country. And we have 6 Max Planck Institutes, which are relevant for astronomy in some way. 2 institutes, one in Hanover and the other one in Berlin, which deal with gravitation. Then another one in Göttingen with solar system research. Then in Heidelberg, we have a Max Planck Institute for Astronomy and another one for nuclear physics. Nuclear physics doesn't really sound like astronomy, but it's also dealing with astronomy. And here we have, I think, the biggest agglomeration of astronomical power. That's extraterrestrial physics and astrophysics. And next door to these 2 Max Planck Institutes, there is also the European Southern Observatory. So really 3 very big institutes next door to each other. Yeah, okay, I'm talking here from Bonn, from the Max Planck Institute for Radio Astronomy, as you kindly mentioned already. And yeah, among the 80 Max Planck Institutes, most are for science, only few for humanity things. And among these 8, there are 6, as already said, for astronomy. And yeah, so let me just try to get this a little bit down. We have in Hanover a system to detect gravitational waves, but it's shorter, the system, than LIGO or Virgo. So that this was never actively taking part in these recent detection of gravitational waves, but the people working there are directly taking part in these detections. So this is a very active experimental institute, while this one is really dealing with general relativity in a theoretical way. I think it's the biggest one in the world on this topic. Then we have here the sun, heliosphere, planets, moons, comets, and also not only solar, but also seismology of other stars. So in a little bit, in a certain sense, it's also expanding out of the solar system. Yeah, then we have here nuclear physics. What are they doing? Astroparticles, physics, neutrinos, for example. And then we have dark matter, star formation, exoplanets, cosmology in the Max Planck Institute for Astronomy. And here we have almost everything collected: evolution of massive stars with numerical simulations of stellar evolution, galactic center research, cosmology, dark matter, star formation, X-rays. And when it comes to the galactic center, you may have heard that in September or October last year, one of the members there, Reinhard Genzel, got the Nobel Prize, 1/4 of the Nobel Prize in 2020 on galactic center research, following the stars circling around the central nuclear engine of our galaxy. Okay, finally, it's the MPIFR. I will talk a little bit about that here in the following. This is a view from the city of Bonn out to the institute, and you have here quite a number of astronomical divisions which belong to the university, like, for example, Peter Schneider with gravitational lensing, weak gravitational lensing, Frank Bartholdi with observational cosmology. We have Pavel Kropa with the initial mass function and dark matter, but actually not really dark matter. It's more against dark matter. And so far, Pavel Kropa and Peter Schneider follow very opposite directions of astrophysical research. And there is also, with Norbert Langer, a person dealing with the numerical simulation of massive stars. We have here some canteen. Yeah, it would be nice. Of course, a canteen in our institute is unfortunately closed. It's all due to Corona and the problems associated with that. We have 4 directors. One is for very long baseline interferometry, observing the continuum mainly. Then he's an ex-director with optical and infrared interferometry. Then we have with Michael Kramer, a person dealing with pulsars and fast radio bursts and gravitation. And we have also Carl Menton, who is dealing with spectroscopy mainly, also including VLBI. So this is something in common with Anton Census on the right-hand side. So yeah, and then we have a little Effelsberg, a little 3-meter copy of the 100-meter telescope for testing purposes. Yeah, so here perhaps this is something to be mentioned as well. These happy young people, this is a picture of the past, of the distant past, one could say. Nowadays, they wouldn't run around like that. They would all have masks on, and they would also clearly be separated by at least 2 meters. So, but this is the International Max Planck Research School where everyone can apply. And the problem is, of course, the limited amount of money. So we cannot take everyone. But this is the a nice way for everyone all around the world to join, say, the University of Bonn, the University of Cologne, or our Max Planck Institute. We are together running this kind of international Max Planck School. So if you have any question, you can of course ask right away, because now I would go to a little bit radio astronomy and not just organizational things. So if you have any question, please come up. So if not, then let's go on. This is on the picture here on the lower right. It's Rainer Mauersberger, who is right now, actually he's doing it since many years, running the show on the International Max Planck Research School. And yeah, I should mention briefly the telescopes we are directly connected to as a European institution. We are, of course, related with the remnants of the European Southern Observatory in Brasilia, which is, however, more and more abundant. Then we are also here dealing with a VLT. It's a Paranal, where, for example, our ex-director, retired director, is getting his data, is still fully working with some of his people. And then we have this kind of jumbo jet flying at an altitude of about 14 kilometers to measure in the infrared sky. We have the LBT in Arizona, southern Arizona, on the Mount Graham, about 3,200 meters high, where there are two 8-meter telescopes connected, as you can see on the picture here, with which are doing some interesting high resolution kind of interferometric work. And maybe you remember the wonderful Herschel telescope, I think the biggest telescope ever sent into space, for infrared astronomy, mainly mapping the dust in the galaxy and in extragalactic sources. Okay, then here comes our home telescope, so to speak, the 100-meter telescope at Effelsberg, only 40 kilometers away from the city of Bonn. Then we have one station of this basically Dutch low frequency array. And this is, this is, for example, our own kind of LOFAR antenna is here seen from the 100-meter telescope down here. This here is a low frequency telescope, so to speak. These are dipole antennas, about 100 of them. And further here, we have the, so to speak, high frequency array, which, however, is also still detecting meter waves and not shorter wavelengths. So that's something which can then be connected all over, not all over Europe, but in parts of Europe. Here you see the center in northeastern Netherlands. And we have here, for example, at Effelsberg, Jülich, Potsdam, Tautenburg, but we also have stations in Sweden, in France, and in England, where these can be connected if required. And I think this is a very interesting low frequency area. Okay, we have more telescopes to choose from, like here the Pico Veleta 30-meter telescope, which is the world's biggest and most sensitive, not biggest, Nobeyama in Japan with 45 meters is biggest, but I think it's the most sensitive millimeter wave single dish telescope. We have here with Noema, formerly the Plateau de Buer interferometry. We have right now 10 15-meter dishes, so that's quite a lot, and this will be expanded. I think the 11th antenna is already under construction. to a total of 12 such dishes. So that's the ALMA telescope of the northern sky, so to speak, even though the sight is, of course, not as good as the one in the Atacama Desert in Chile. We have very good access to the VLA here in New Mexico and to the VLBA going from Hawaii to the Virgin Islands. And yeah, to the Green Bank, the other 100-meter or a little bit, I think 105-meter dish in the US, which can also be used and which is a little bit more sensitive for spectroscopic research, while it is more problematic for polarization studies than the Eversberg telescope. So it's a different construction here, and you see that here the focus is at the side and not at the center. So this means that the entire dish can be used to collect data different from that or different from Eversberg, which is built in a similar way. And this gives you a larger surface and also gives you a higher sensitivity for spectroscopic measurements. However, when it comes to magnetic fields, where you need a real symmetric telescope, then this is not so good. So it's very nice because this is a very good alternative. It can do certain things better than Eversberg, and other things Eversberg can do better. So it's a very nice, interesting complement. So the two are not really doing exactly the same. Yeah, and then let's go to Chile. We have the Atacama Pathfinder experiment. That was a pathfinder for the ALMA, for the big ALMA telescope, with one 12-meter telescope at an altitude of 5,100 meters. And this is ALMA itself with 30 to 40 12-meter antennas and 9 7-meter antennas, which is state of the art, and which is personally for me my working horse, even though I have to say it's extremely difficult to get time there. And I think now, after 2 years, we have on the 20th of April the first deadline again, and I would expect that there will be more than 2,000 proposals. And you can imagine that not everything can be accepted by such a large number. Okay, this is, if you have no questions, please interfere if you have, because now I'm going into some radio astronomical details. On the right-hand side here, you see a waveguide. I think it's a horn used, if I remember well, it's at Green Bank for the first detection of the first spectral line at radio wavelengths. That's a 21 centimeter line of H2, H1. And yeah, so this is a kind of waveguide, a kind of horn where the radiation goes in to a sensitive radio receiver, typically a cryogenically cooled solid state amplifier with very low internal noise. And after an amplification by perhaps 15 orders of magnitude or so, you get your sensitivity, which means typically 10 millijansky have 10 to the minus 28 watt per square meter per hertz. Yeah, perhaps I should mention here also that at radio waves, there is something quite simple. And that is, if you are in the Rayleigh-Jeans limit of your Planck radiation, black body radiation, then it's nice that the intensity you measure is proportional to the temperature of the source. This here is written in terms of frequency. This is the same, but written in terms of wavelength. So this is, then there is a proportionality between intensity and temperature. So you can express everything in temperature. And I should also mention, because we see that later, that dust intensities of dust are a little bit different. That's not a Planck curve, but it's something, a modified Planck curve. So you see here the new frequency squared, and there is another factor coming in. another exponent. And this beta is depending on some properties of the dust. So you cannot say it's exactly 2 or so, but it might be something between 1.5 and 2 at radio frequencies or sub-millimeter frequencies. So you get something like frequency to the 3.5 to 4, a very steep rising intensity curve you will see later on in one of the slides I will present. Okay, so the system temperature, first you get some power from the target, and you get this power, and this has of course to do, as previously told, with the temperature. And you also have, and that's a problem, you have in your system, you also have some power, which also creates some noise, and not only your source, and so that you get something more than the radiation simply merely from your source you want to detect. And therefore, and this is a problem I cannot see right now, because I have here a, because it's blocked and I don't know how to get rid of that. Anyway, yeah, you see here, there is an incredible amount of different kind of components. And I cannot see that right now on the screen, but I remember that there is, for example, the cosmic microwave background, CMB. There is spillover from the ground, which also makes some noise. Then there is a calibration signal, which is also put into the system and which makes everything a little bit noisier. And yeah, the source is of course also there, but there is an awful amount of waveguide noise and receiver noise. All this comes in and has to be accounted for. And all that should be minimized as much as possible. Yeah, how do you do the calibration of these data? You, at centimeter and decimeter wavelengths, you introduce some additional noise, even though you don't like it, but you have to do that at certain phases of your observations so that you get your source with this noise diode and without that noise diode. And if you can, on calibration sources, determine the intensity, the temperature of your noise diode, then you can calibrate your system. These calibration sources are, for example, the planetary nebula NGC 7027 or the quasar 3C286 at redshift, what was it? I think 8.8 or 0.9, something, almost 1. These are excellent calibration sources which do not change. At higher frequencies, however, where the atmosphere is more and more coming in, you use a chopper wheel, that's to say a wheel which has some holes, and sometimes when it turns around very fast, you get the sky, you have a direct connection of the receiver to the sky, or you have this kind of chopper wheel in front of you, which provides some additional kind of temperature, and you have two temperatures, for example, liquid helium, not helium, but liquid nitrogen at -77 degrees, and then you can compare the two, and then you can set up a very nice calibration. That's actually, from the point of the observer, even simpler than the noise diode. Okay, and important also, telescopes are being built in a homological way, so they are always parabolic, but the parabola changes. That means that the focus, the location of the focus is changing. But on the other hand, there are with it some other things. The total shape of the telescope changes. So the telescope gain depends also on elevation. It makes a difference whether, for example, the Eversberg telescope is looking at a source at 80 degrees elevation or only at 30 degrees elevation. And the telescope is optimized at about 30 degrees elevation, so that at very high elevation, you get lower signals, slightly lower signals, depending on the frequency. If you observe at a high frequency for the telescope, the effect is significant. If you observe at low frequencies, you don't have to care about that. Okay, so we have 4 different kinds of temperatures. I just show you the antenna temperature, the incoming signal. TA star is the antenna temperature corrected for atmospheric effects. Then we have the main beam brightness temperature. That is the temperature of the source if the source would cover the beam size of the telescope in an even way. And the TB is a real brightness temperature. So for example, imagine only 1/1000th of the beam is covered, then you may get a main beam brightness temperature of 1K. But since in reality, only 1/1000th of the beam is really covered by the source, the real brightness temperature of this tiny source is not 1, but 1000 degrees. And this is, for example, quite important for certain continuum radiation from active galactic nuclei, or also from, for example, maser lines, which have temperatures of so-called temperatures of brightness temperatures of 10 to the, up to 10 to the 15 K. Okay, the question is, we should, I think I should talk for half an hour and then we make a 5-minute stop. Is that right? And when is this happening? Is that in 5 minutes or so?
Yes, Professor Henkel. You can now continue to up to 9:10 and then stop for about 5 minutes and then you will start again.
Bit faster, I should mention here the local oscillators. So you get, for example, a high frequency, but in order to really amplify that by 15 orders of magnitude or so, you have to do something with it and to push them down to lower frequencies. And that is, you mix it with other radiation, and then you get the difference between this inserted signal and your real sky frequency. And if these are only a few gigahertz away from each other, then you are fine. Okay. Yeah, it works. Great. Okay, so observing methods, frequency switching, that means you switch the frequency back and forth, and you get such a spectrum. And after folding this, you get this kind of thing. You can do position switching, where you measure your source, and then you measure an off source where there is nothing, and you compare the two. And then you wobble with a rotating horn, and this is very fast, and then you get very good baselines. So frequency switching brings you 100% of the time on source, but it has some certain problems also with respect to baselines you get, and also the mathematics of the folding, which you should investigate it. Then position switching is intermediate. It's 50% of the time on source. Baselines are of intermediate quality, and you should find a good offset position and comparatively simple to analyze. And then wobbling rotation horns, that's best baselines, and also 50% of time on source, but you should not have extended sources because the wobbler cannot go too far away from the source you really want to see. Okay, caveats. Yeah, I think these are typical questions. What's the central channel of a spectrometer? Should some parts of the spectrum be avoided? Check the way the data reduction program is handling folding for frequency switch data. In case of position switching, is a reference position really free of emission or absorption, so that your comparison, you really compare your incoming data with blank sky? And then how are the velocities defined? Radio astronomy provides you with radio velocities, which are more accurate than I think in any other kind of electromagnetic part of the spectrum. And yeah, so the radio convention, there is an optical convention, there is a relativistic convention, and then there is also, how to say, there are also different kinds of frequencies, in the sense that there is a barycentric system, there is a heliocentric system, there is a local standard of rest system. So all that counts and leads to uncertainties. For example, if you have a rest frequency of 1 centimeter, wavelength of 1 centimeter or 30 gigahertz, and you have a velocity of 30 kilometers per second, then depending on radio or optical definition, you have already a difference in the velocity of 3 meters per second, which is sometimes too much already. Yeah, then how are frequencies, channel spacings, and all that stored in the data files, and do only differential measurements? Observe always the lines in question with a short time interval and compare it with a blank sky. So sometimes it's getting a little bit tricky, no matter whether the line is seen in absorption or in emission, whether it is thermal or a maser. Specialization on 1 or 2 instruments may be a good idea, because otherwise you are running into too many unknown problems. Okay, so now let's come to some astronomical highlights. That's to say, first, some more explanations. And that is, I told you already that the brightness is going with the square of the frequency in the Rayleigh-Jeans limit. And you can see that the higher the temperature, the longer Rayleigh-Jeans is valid for a black body radiation, but at some higher frequency here to the right, then it breaks down, and you should always be aware to be in the Rayleigh-Jeans limit. Otherwise, you have to apply the full Planck equations. Then, for example, here you see the moon, which at radio frequencies is behaving like a perfect black body. The quiet sun at a temperature of 5,600 K or so also, but the active sin, like Jupiter, for example, when there is some activity, you have a high, very high intensity at very low frequencies. Synchrotron radiation leads to reduced fluxes with higher frequencies. So, for example, Cassiopeia A, supernova remnants, Cygnus A, probably galaxy with vast radio jets, the Crab Nebula, Virgo A, and M87, we get to that, or even M31, the Andromeda Nebula, or here's the most nearby quasar. They all have this kind of synchrotron radiation, and this decreases with different slopes with higher frequencies. On the other hand, we also have H2 regions, and these are rising like a black body when the temperature is, when the optical depth of these regions is high, but when they are at higher frequency are getting into the optically thin region, then the flux density is falling down, or is almost constant. So exponent of the frequency is only minus 0.1. So it's very slowly going down. And here you can see, for example, at a nearby starburst galaxy about 4 megaparsecs away from us, that you have here 3 different components. These are the measurements here. And you have here the synchrotron fraction, a very steep one, minus 1.4. Then you have the free emission from the star-forming regions, from the H2 regions. And then you have, as I told you before, this very steep rise from the dust, which is dominating here the emission at higher frequencies, going into the sub-millimeter range. This here is a wavelength of 10 centimeters, and here this is a wavelength of 1 millimeter. So if it goes below 1 millimeter, you have dust. Okay, so here is atmospheric condition at a site like Bonn or Effelsberg with this kind of H2O line, which still does something, but it's not too terrible. It's a Sierra Nevada or in the Alps. This line is very tiny, but you have other lines from H2O which disturb you. These 2 lines here, these 2 absorption lines are from O2. So the transmission goes down from O2 basically at all altitudes on Earth. So when you go to very high mountains, this will not change, but the H2O component will change. And this is what you get in the Atacama Desert or on Hawaii with 4,000, 5,000 meters. And there you can even see here at 650 or 850 gigahertz, some lines. So these are nice windows where you can do interesting kinds of astronomy. With a SOFIA instrument, of course, with a SOFIA jumbo jet, of course, you have an even better sky at 14,000 meters, where you can then observe even farther out, but in frequency. But on the other hand, the telescope there is, of course, not as large as what you can build on the ground. Yeah, so radio emission is great because the waves are so long that there is no obscuration by dust, and interferometry allows for observations with the highest angular resolutions. Let's come to some scientific highlights. So, for example, when it comes to synchrotron radiation, we have here CAS-A. I think it's a supernova which would have been visible around 1690, but it was not seen because it's probably buried in the galactic plane, too much dust in front of it. So it was first discovered in the radio. It's, I think, one of the brightest radio sources in the entire sky. And thus a very prominent source, which was discovered, I think, already in 1948. And later on was investigated. Similar synchrotron radiation you can also get from other sources, from extragalactic sources, Cygnus A, for example, here, which was for a long time an enigma, because these kind of double radio sources were kind of totally unknown before, especially because optically, all what you see is this tiny galaxy here in the middle, and all the rest is invisible. Now we know that here there is not only an active galactic nucleus, but there is also a second one, which is at a distance, a projected distance of about 460 parsecs. And probably the interaction of these two has created these enormous jets here with compass about 160 kiloparsecs, which is enormous. By the way, we are now trying to carry out with VLBI absorption lines, molecular absorption line studies towards the nucleus, which is much, much tinier than what is shown here, to see what's causing this activity. So pulsars is another thing. Typically in radio astronomy, one was joking that if you are not working on pulsars, you have no chance to get the Nobel Prize. So this is, for example, I think Lyndon Bell discovered the pulsars. Hewish got the first Nobel Prize. Here with Hulse and Taylor, they discovered this binary pulsar, so where they could then figure out that the orbit of the pulsars was getting narrower and narrower. So they were orbiting each other faster and faster. And also the shift of the perihelion could be seen. So exactly as predicted by the theory of general relativity. So in other words, this was a big jump into kind of regions with very strong gravity. This was totally new and certainly worth the Nobel Prize. Another interesting thing are fundamental physical constants, and here the electron to proton mass ratio. We have here a face-on galaxy at a redshift of 0.9, absorbing the continuum of a background blazar, and this background blazar is because of this foreground galaxy, which is face-on. It is gravitationally lensed, leading to two main images of this blazar. And you see here at K 2 microns, this one is bright, so it's not highly obscured. And this one is not so bright, it's highly obscured. And here you see lots and lots of molecular lines. About 40 or 50 molecular species have been detected here. Here also some, but only some. And you see here, this northeastern one corresponds to this radio peak, and the southwestern one to this radio peak here. And you get an enormous amount of molecular lines, and some of these molecular lines are behaving differently with respect to the electron to proton mass ratio than others. That's to say, there are molecular lines like those from methanol or from ammonia, which show a different kind of behavior with respect to electron to proton mass ratios as HCN or HCO+. And the different behavior means they change frequencies. Their frequencies are depending on the electron to proton mass ratio in different ways. So if the electron to proton mass ratio would be different at a redshift of 0.89, then you would see different radial velocities for the different lines. And since we do not see this effect, we can say that at about 7.5 billion years ago, the electron to proton mass ratio was about the same, to an accuracy of 10 to the minus 7 to 10 to the minus 8. H1, the 21 centimeter line in interacting galaxies, is a great thing because you see all the interaction of the gas phase of these galaxies. Here, for example, that's a typical case of interacting galaxies. Optically, you see nothing, but here's M81, M82, NGC 3077, and somewhere here's also NGC 2976, but this has not been studied, even though it's also connected, I think. And here you see the H1 distribution, and you see that these galaxies are all connected, that they are interacting heavily. And for example, here, even some dwarf galaxies have been found through that, one even showing a lot of dense, relatively dense molecular gas. Yeah, and this is another interesting feature. This has been obtained with the Atacama Compact Array, not really with a full ALMA telescope, but only with the 9 7-meter telescopes, which are also there providing short baselines and relatively low sensitivity and relatively low angular resolution. This is a galaxy NGC 253, about 3 to 4 megaparsecs away from us, a starburst galaxy, and you see an incredible amount of lines. Yeah, this is only the start of it, because these are 9 7-meter antennas, but we have also 40 12-meter antennas, and they will provide even much, much higher sensitivity than what is being shown here. So there is some work to be done on this. Yeah, and then we come to low mass star formation, dark clouds. I think these are CO maps of the torus molecular clouds, some area there. And local cool little turbulence, extremely narrow lines. These can also be used to measure, for example, the electron to proton mass ratio there. And it's the same as in the local labs, to about 10 to the minus 9. And then we have free radiation here, as I mentioned it already before, in regions of high mass star formation. Here, W51, which is a very prominent star forming region, at a region where we see tangentially toward the spiral arm of the galaxy. And the distance to this very interesting object is about 5 kiloparsecs. Okay, and then, maybe you remember Betelgeuse, which got weaker recently, I think because of ejected dusty material. But let's focus instead here on the late type stars. Is another very interesting part of radio research, because you can look through these molecular dusty shells into the inner parts of the stars, and you can measure these dusty shells very well. But let's go to the Orion Nebula instead. There's the strongest molecular line visible at Effelsberg. These are 2 spectra here being taken. And this is if you observe with very long baseline interferometry and with very high angular resolution. Therefore, you resolve it in an awful amount of components, always different radio velocities. And you can get a statistical parallax even with it. You can see how these single blobs are moving out our common center. But you can also use these strong components, these are really very strong, to get parallax measurements, so that we know nowadays that Orion is at a distance of about 410 to 420 parsecs. 100 years ago, Van Manen was pretending more that he had seen the proper motion of M33, the triangulum galaxy. It was a fake measurements, apparently. He had not seen it, as it became clear later that this was a distant galaxy at about 700 kiloparsecs away from us. But in the meantime, we succeeded in getting the proper motions of two H2O masers. One is IC133, and the other one is an M3319. And we could measure here the proper motions. You should see here that this here from here to here are 100 micro arc seconds. So it's 1/10 of a milli arc second. And this, together with a good dynamic kinematical model of the galaxy, then you can determine even the distance to the galaxy independently. And especially what you can do is to measure the dynamics of the local group. We now have the vector of IC10 and of M33. What is still missing, however, and that's the most important thing, is a moving vector of M31, the Andromeda galaxy in space. We know the radial velocity, which goes toward us, but we don't know how much proper motion it has. And we are working at it since many years, but it's a very, very difficult topic. I can talk more if you have questions asking on that. Yeah, then black holes, accretion disks, and the Hubble constant. So for example, here is a very nice galaxy NGC 4258. It looks normal, perfectly normal, but not if you look into H alpha or into the radio continuum. Then you still have here the spiral arms, but you see another spiral here. And this is a jet coming out of the very center. And when you look at this, then you see in H2O, 22 gigahertz H2O line I showed you already before, that there are some systemic components, then there are some components 1,000 kilometers higher in radial velocity, and some components 1,000 kilometers per second lower in radial velocity. And this can be explained by a rotating accretion disk with the systemic things here, with the red shifted items here, and with the blue shifted here. So turn this around, and this explains this kind of galaxy. So we have other galaxies much, much farther away showing the same kind of pattern, and these can be used because these blobs, these H2O blobs, are flying around the central nuclear monster in Keplerian orbits. We can get the size and shape of nuclear accretion disks. We can determine from the Keplerian orbits with simple Newton's equations the mass of the supermassive black hole. For example, for this galaxy just shown before, it's 40 million solar masses within 0.1 parsecs. Then the precise determination of the Hubble constant, because with that you can also get the angular size distance to these galaxies. For this earliest NGC 4258, it is 7 megaparsecs. And finally, with the Hubble constant directly determined, you can also constrain the rotative dark energy. And these measurements are a part of this growing discrepancy between cosmic microwave background Hubble constants, which are requesting values below 70 kilometers per second per megaparsec, and these measurements here from the local universe, which are requiring a little bit higher values, a little bit above 70 kilometers per second per megaparsecs. This is a growing discrepancy, which, if it turns out to be real, would provide some additional new, very deep insights into our universe. So now that's the second last slide of this talk. That's the Event Horizon Telescope, what also in our institute is very busy with that we are trying to use VLBI not only at low frequencies, but also at high frequencies. At 3 millimeters, we have already a normal setup, but in the meantime, it's also going to 1.3 millimeters. And the goal is 345 gigahertz. That means it's about 0.8 millimeters wavelength. And with that, you get horrendous angular resolutions. Okay, almost like using a satellite. And with that, you can look at the center of our local galaxy supercluster, the Virgo A galaxy, or NGC, what is it, 4486. And yeah, you get with ALMA, for example, here something like 1300 light years across. Then you get with the BLBA, you get 0.25 light years across. And here you get with this Event Horizon Telescope, you really get a picture of the black hole. It's interesting that you can get a black hole from M87, but not from the galactic center itself. The reason is variability. This here has a black hole mass of about 6 billion solar masses and has therefore an event horizon diameter of about, what is it, maybe 10, 15 or 20 light hours. And our galactic center nuclear engine has about 1,500 times smaller mass and therefore 1,500 times shorter, smaller event horizon diameter. So that therefore the variability of our nuclear engine in the Milky Way is extremely high. You can have twice the flux density within 1 hour than before, and then you cannot get, if you integrate over several hours, decent images of our galactic center anymore, because the galactic center looks at the beginning and at the end of your observations totally different. And this is a big problem. You can only solve that by the addition of many, many telescopes, so that you can almost get instantaneously a nice, decent, very long baseline picture. And this is something for the future. I think they are building already a telescope in Greenland, which is, of course, not very suitable for our galactic center, which is in the southern sky. But there is some motion going into that direction. So this M87 is about 2,000 times more distant than the nuclear monster in our galaxy. And it is about 1,500 times more massive. That means it's a little bit smaller. So from our galactic center, you would get a black hole with a slightly larger Schwarzschild radius. In our galactic center, you would get about 10 micro arc seconds, while for this source, it is about 7 micro arc seconds, I think. And still, it could be resolved to some kind. And this, I should also mention that this picture exactly fulfills the expectations. So with this kind of nice radio picture, I want to finish. This is, I think, at 230 gigahertz or 1.3 millimeters. This was obtained. So, thank you for listening to my talk. And I'm having here in the next very last slide a list of all the, or many of the interesting features which can be dealt with radio astronomy. Some of them I have not touched because, of course, this cannot be complete. Radio astronomy is too large and too wide to mention everything within 1 hour. Thank you very much.
Thank you very much, Professor Henkel. ملهم، هل عندنا برومو ولا؟ ملهم. Anyway, thank you very much for this wonderful talk and the wealth of information that you shared with us. wonderful talk and the wealth of information that you shared with us. As you said, astronomy is a big field, and it's very difficult or impossible, I mean, to cover it in one talk. Therefore, we are looking forward to having you again to discover some, I mean, fields of radio astronomy. I have a question for you. How can we use radio astronomy in investigating protostars?
Radio astronomy is insofar very good because protostars are surrounded by dust. And when it comes to dust, optical measurements fail because they cannot look through it. And UV and X-rays are also a problem. Actually, X-rays might work, but X-ray measurements, in spite of Chandra, have not the angular resolution you can achieve with radio astronomy. Chandra brings you a 1 arcsecond resolution, which is the best I think you can get at X-rays, while at radio waves you can get a very, very high resolution. Actually, there is this Russian satellite, Radio Astron, even flying, or it was operating, and we got with that angular resolution, even though toward the extragalactic object, but I suppose the same has been done also for galactic objects, of 8 micro arcseconds, which is quite amazing. And I think it's a world record right now of observational resolution. But even say with the VLA or with the VLBA, you get to milli-arcsecond resolutions. And therefore you can study very carefully what's going on inside of this highly obscured star-forming regions. Okay.
Is there any connection between these star-forming regions and the masers that you are detecting?
And what am I detecting? I didn't hear it.
Maser line.
Oh, yes, definitely. It is star-forming regions. If they are low mass, have very often no maser lines. If you have high mass star-forming regions, they almost always have maser lines. And these maser lines provide very useful things because they are very strong and they are very compact. And so they can be used to pinpoint locations. And therefore you can measure, for example, parallaxes. That's in our institute by Carl Menton. One of the main projects of his directorship is to measure parallaxes of many, many galactic star-forming regions and also of Lie-type stars. And so you can measure the distances, and this has led to a smaller galaxy than previously expected. And I think with the sun rotating faster around the galaxy than expected. I think typical papers or the classical papers on this are from Mark Reed, R-E-I-D. If you look into that, you can find the most recent results.
That's great. We have Dr. Yasin Mbleki. He wants to ask some questions. So please, Dr. Yasin.
Yes, good evening, Professor Henkel. Do you hear me?
Yes, very nice.
Thank you very much indeed for this wonderful lecture. It's really amazed me. I am actually a solar physicist, and for the last 5 years been working on exoplanets. And
very exciting area, yeah.
Yes, and we have a telescope or a couple of telescopes in Atacama, in Paranal, in Chile. We joined, ESO, and we participated in TRAPPIST You've heard of TRAPPIST-1 discovery.
The 7 planets, are there
Yes.
still 7 or are there more?
I think they are becoming more, yes, indeed.
Wow.
So, yes. So, I mean, you have wonderful telescopes and observatories around the world. One of them is ALMA.
Mhm.
And one of my students is asking me, so I'm asking you, how do you observe exoplanets via radio telescopes? And by the way, I want to thank Dr. Abdurrahman Malawi for this opportunity to have you with us. Thank you very much.
Okay. Yeah, thank you for your question. I think I think a few years ago, I was at ASO for a month, and there I got into contact with some people doing exoplanets. And I think we wanted, then I left, so I was not participating in it, but we tried to look for planets which are eclipsing very partially their parent sun. I think like the 7 previously planets of TRAPPIST-1, and then looking for atmospheric lines like O2 or N2 or CO2 or something like that. I think that's one method how to do some radio astronomical measurements.
Exactly, yes. Thank you very much. Thanks a lot, Prof.
Thank you, Dr. Yassin. I think there is a question here, Professor Henkel. The question is the proton to electron mass ratio important as much as the Hubble constant? This is one question from one of the audience.
Very interesting question. I've never thought about that, but I think we are looking for ways out of the standard model of the universe. I think we have general relativity on the one hand, and we have the laws of particle physics with the particles, with the Higgs boson on the other hand. And quantum mechanics and general relativity are not matching each other. So one could imagine that at least one of these 2 theories is wrong. And yeah, but which is wrong and why it is wrong? And so we are looking for possibilities to get across the present, the present limitation. And one limitation is the constancy of constants. There are many, many models which predict variable constants depending on time and location. And this is then for the proton to electron mass ratio, something very, very important. The other thing with the Hubble constant, whether this would be, if there is, first, we do not know with absolute certainty whether there is really a discrepancy between the near universe Hubble constant. Excuse me, I have to charge my laptop. So it continues. So with a Hubble constant, we are not totally sure whether there is really a discrepancy. I think this has to be clarified a little bit more. And if, I think then the reasons for it could be quite different. For example, one assumption with a Hubble constant is if you observe the CMB, the cosmic microwave background, is that the universe is flat. But is it really flat? We don't know that. We know that it is flat to, say, 10 gigaparsecs or something like that, but I think not more. And so when people normally say the universe is flat, then this is a very poorly constrained fact and should be, I think, we don't know very much about the flatness of the universe, and this is certainly something to go for.
Okay, I think there is a question, it's a technical one. Somebody is asking, what are the most important parts when it comes to designing a radio telescope? Is it the dish or the cables, or what the most important parts of the designing a radio telescope?
I think the dish is the most important part because it's the most expensive part. Receivers are also expensive, but actually it's one receiver is certainly a small thing with respect to an entire telescope. So I think it's a telescope itself. And when there is a really good telescope, which has unique properties, then the rest will be agglomerated almost automatically. An exception to that is perhaps this low frequency array centered in the Netherlands, but with some German and some other parts. These dipole antennas are pretty cheap. Yeah, so I think the entire thing at Effelsberg, the entire station, I think was costing less than 1 million euros or $1 million. So this is maybe a very limited investment, and therefore probably so many other countries have gone into that. But normally it's a telescope, which makes a difference.
Right. And how can we use, the radio telescope also in investigating our own galaxy, and the rotation, curve of our galaxy?
Oh, you mean the rotation? Yes, this was with the rotation of the sun around the galactic center and the size of the galaxy, you mean? This was with the Bessel project, which is still ongoing, where the distance to many, many H2 regions has been measured. For example, there is one H2 region, W3OH, compact, ultra compact, even H2 region. And everyone thought it was at 3 kiloparsec distance, but it was only at 2 kiloparsecs distance. So that's a huge discrepancy. And such things came out in very many of these measurements. So the galaxy really got smaller through the measurements. And I think this is limited right now. As far as I know, the most distant parallax measurement is from 20 or 21 kiloparsecs distance. That's a source which is behind our galactic center at the other side of the galaxy, and at about the same distance as the sun from the galactic center. And you can imagine what kind of parallax is needed for that. For 1 parsec distance, you get a parallax of 1 arcsecond. For 1 kiloparsec, you get 1 milliarcsecond. And for 20 kiloparsecs, you get a parallax of 50 microarcseconds. So that was really something exceptional. And I think this is about as far as we can go on Earth. And if we want to get further with parallax measurements, we have to go to space.
Okay, Professor Henkel, thank you very much for this wonderful talk. And as I said, we are looking forward to having you again in another field of radio astronomy, and even in star formation, because you are, expert in star formation as well.
I would be delighted.
So thank you very much. I think that is for tonight. Thank you very much for everybody who are with us today in this wonderful, occasion. And we are looking forward to see you again. Thank you very much.
Yeah, wonderful. Thank you.